Right, we're carrying on with this waves light worksheet. Let's do a few things. So this here is your boundary between glass and air. If you draw a perpendicular line, that is called the normal. Right, now watch this. You've got a ray coming in and you always measure it to the normal. That is the angle of incidence. So it's measured to the normal. So this is that's your incidence ray, or ray of incidence. Incidence ray. How would you define that? That's the incoming ray. Right, angle of incidence is the angle between the incoming ray and the normal. Right, excuse the dingy writing, it's a bit bent, but what else do you need to know? Right, what color can we use? Green. So now this is the ray that's gone through. So this here is the refracted ray. And if you notice, it's bent. Let me just take this. So that's your normal continued. It's bent towards the normal. So this angle here is the angle of refraction. And this is known as the angle between the refracted ray and the normal. Right, it's gone from it's not obvious color, is it? It's a bit silly. Right, it's gone from a less dense medium to a more dense medium. So it will refract, it will move towards the normal. So when this is the case, this angle is going to be smaller. Okay, what else do we need to know? What I'm going to do is, maybe I should do it like this. You can have air, glass, air. So here's a ray, it comes in. Let's try to do it in such a way, yeah, so that's your normal. blue is blue. Right, so that's your angle of incidence. In, oh my god, I can't spell. Into, I can't spell. I was going to put index or indices or something. Incidence. This here is the incidence. How call is that? Incident ray. Right, should I just, okay, what I'm gonna do is I'm gonna change color. So now it's gonna bend there. Gonna go back, draw a normal here, perpendicular. Right, I'm gonna go back, label this to the normal. So this green ray is called the refracted ray. It's called the refracted ray, and this angle here, I'll call that angle X, is the angle of refraction. Right, and then when it comes, what color? No, let's use that one. And then it's going to bend away again. Yeah. So what's happened is, let me get this right. So your rays come in, it's refracted towards the normal, and then it's refracted away from the normal. And hopefully that angle and that angle, or that ray and that ray, should be parallel. I think that's more than enough for you to know. Right, so what I'm going to do is I'm going to delete all this. Should we delete all that? No, we won't. What we'll do is we'll keep this bit. No. Hello. It's there you go. So what we'll do is we will keep that here for future reference. In the meantime, we can delete all of this stuff just to clear up the right. Measure the angle of incidence. So that's the incident. Where are we? Let's put that there. Incident. Put that inside incident ray. And you always measure it to the normal. So you need to measure that angle. And when you measure it, it should be, hopefully, 51. So it's quite clever the way they've done it. They've done it in a way where you need to think about it. Right, state the formula linking refractive index, angle of incidence, and angle of refraction. So angle of incidence, I, angle of refraction, R, right? So the refractive index, it's a measure of how much light bends when it goes through an object. Refractive index, he says, is the sine of angle I divided by the sine of angle R. So angle I, angle R, angle of incidence, angle of refraction. Right, okay. The block has a refractive index of 1.52. Use the formula to show that the angle of refraction is about 30 for the ray at point K. So they've said to you the angle of incidence is 51 degrees. That's from there. Right, so what they've done is, let's go through this. That's gone over there. So what you do is you write refractive index is 1.52 equals the sine, they've given you that, the sine of 51 degrees over the sine of R. Remember, they want you to write this out. Then they want you to rearrange it. So we put sine of R equals sine of 51 over 1.52. You're just rearranging it now. And we put R equals inverse sine right, according to the mark scheme, look at this carefully, so just bear this in mind here, and you've got to work within their parameters here. They've said that equals, when you put that into the calculator, equals 0.511 and so on. So even if you put like 4 or 5 decimal places, it's fine. And then R equals 30.7 ... degrees. So you worked out that this here is 30.7 degrees. They gave you that, and they gave you the index, right? Okay. Right, the refractive index is 1.42. Calculate the critical angle. Right, so what you do is, there's a formula, is the sine of the critical angle is 1 over n. And let's get this right. Yep, that's the formula. We're trying to work out this. That's just 1. N is sine I divided by sine R. We know those two, so we do sine, well, to me they've given, yeah, they've given us that. I'm trying to work out too much. They've given us that. They've given us that as 1.52. So we can say sine C equals 1 over 1.52. Right, so write that down, rearrange it, Yeah, do you know what I would be? Let's just go one step further. 1 over 1.52, let's write that down. 1 divided by 1.52 equals that. So we can say 0.6578 dot dot dot. So then we write down c equals sine to the minus 1, because students always get this bit wrong, so they're really fussy, and rightly so. Right, so then we're saying c equals okay, they've gone to the nearest 1 degree, 41.1, which is 41 degrees. The reason is because they're giving it to the nearest whole. Yeah, so that's what you've got to happen. That's what you've got to do. So calculate the critical angle is 41 degrees. Right, next one. What happens to the ray at point L? Where's L? Right, okay. So what's happened? The ray's come in, it's bounced off, and it's come up. So it's been totally internally reflected. So one marker. So all the one you can say is you have total internal reflection. So you can say the angle of incidence is greater than or more than or above the critical angle, so it reflects. There you go. Right. What I want to do is just go through this one thing before I'm not gonna answer that here. Just bear with me 1 second. Just want to go through this. This is quite good. Right. 1, 2, 3. So this material here just try to understand this. This is glass. This, can we zoom out? Yeah, okay, maybe one more. Okay, there you go. Right, so what I'm going to do is I'm going to draw the normal. Normal. Right. So you've got a ray coming in. Right. This here angle is the angle of incidence. And then the ray continues on out that way. And then you've got a weak reflected ray. Reflected ray. So this is the angle of reflection. Right. So now I'm going to change this angle here. I'm going to make it bigger. So my angle's coming, my ray's coming in there. Incident ray, or ray of incidence. Incident ray, we'll call it. Now, so that's coming in, and that's the critical angle now, because I is big enough for total internal reflection to occur. Yeah, so these two are the same. So where I incident ray equals reflected ray, it's called the critical angle when you get total internal reflection. This ray is a strong refracted ray. Okay, right. So this ray now is gonna run along here. It runs along so the refracted ray runs along the boundary, because remember this is glass here, and this bit here is, just say air. Right, now if I, where's that, there it is. Right, if I now go even further, if I make it even a bigger angle of incidence, this is also I, this is a strong reflected ray. So you got total internal reflection. I just want to show you that. So these diagrams, if you can learn them, so if this angle is less than the critical angle, you get refraction and some reflection. If they're both equal, you get a reflected ray, and the refracted ray runs along the boundary, and then beyond that, where the angle of incidence is bigger than the critical angle, you get total internal reflection. So you get total internal reflection. Right, but the difference between this and this, some of the light will travel along here. So this ray is not as strong as this ray. Okay, right, we'll call it quits there at that.